discrete random variables. So that's part 2 here. And I want to write first of all, a few formulas. Suppose that x is a discrete random variable. I will abbreviate this by using DRV. And f sub x is its density. Now, what is the significance of the density? And what is actually the definition of the density? The density of x, that's the definition actually. Let me write it. Let me stress that because I don't think I stressed it strong enough last time. Of x. F sub x is the unique function satisfying the following property. The probability that x takes values between a and b is equal to the sum of the values of the density function when x is between those values. So in short, what does this formula say here? This formula says that if you want to find probabilities that the values of the random variable, the probability that the values of the random variable will be within a certain range, then what you need to do is simply look at the density function and sum the values of the density function for whom the lowercase x, the value of the random variable, fits the requirement that it's between a and b. Okay, with discrete random variables, this has to be inclusive to avoid mistakes. So that is something that we really need to look at. Of course, this property implies that if you sum every value of x, so if you say what is the probability that the values of the random variable will be between negative infinity and plus infinity, well, that includes all the values of the random variable. That should be equal to summing all of the values so x exhausts all the values of the random variable x, and therefore this should be equal to 1. Because the random variable will take one of the values within its range. Okay? So this is the significance of the density function. Here, x runs throughout the values of x, the range of x. I put it here with words so there is no confusion. And let's do some examples now. Today we'll also do our first example, the binomial distribution. It's very, very important. I will start with the Bernoulli random variable. So here is the Bernoulli random variable. That will be my first example. The Bernoulli random variable takes only two values. Success, you can interpret one as success and 0 as failure. And if I say that the probability that x takes the value 1, that is the density of x at 1 is equal to p, where p is a positive number between 0 and 1, then the probability that x takes the value 0, that we have a failure, will be 1 minus p. Because x can take only two values. So we can have only one thing based on what we mentioned here, that guy here. That thing that I circled is telling us that if you sum the values of the random variable, the values of the density function that correspond to the values of the random variable, this tells us to sum only two terms, the value of the density for 0 and the value of the density at 1. And those are the only two values random variable has, so we only sum two terms. That should be, the first should be this, but the second is p, and that equation that I have here implies that the value of the density of x at 0 is equal to 1 minus p.
Question.
Yes.
Why is your range for p not inclusive for 0 and 1?
I just wanted to avoid any, it doesn't have to be, it can be 0 or 1, yes. It can be 0 or 1, just wanted to avoid the trivial cases that at this point would cause more confusion. So the parameter p here is, which is the probability, can be between 0 and 1 inclusive, both inclusive. Okay, here you have your first model of a density, of a density actually, of a random variable with a known density. So when I say that I have a Bernoulli random variable, automatically you understand now what is the density function. The density function is given by the equations that I have here. What is the only value that you need to know in order to fully know the value, in order to fully know the probability model of the random variable? Well, it's the value of this parameter p, which is the rate of success, the probability of success. So p is the parameter that fully determines the density of a Bernoulli random variable. If you know this, then you fully know the random variable. Okay? That's what you need. And here I have one example. So this is a very useful random variable. Politicians run polls and they try to see if they will win an election or if they will lose an election. What do they actually do? They win an election is success. Lose an election is obviously failure. So they have a Bernoulli random variable. What are they interested in? They're interested in the density function, namely, they're interested in to this parameter p, which is the rate of success, the percentage with which they will be elected. And what do they try to do to find out? Well, we do polls, we do statistics. We go out and ask people, a subset of the public, for their opinion about the candidate, and we find how many are in favor and how many are not in favor. And from looking what the rate of those who favor the candidate within the subset, we try to extrapolate what is the value of the parameter. That's exactly what a typical example of parametric statistics. And we will do that later in this course. That's estimation of proportions. So when we do parameter estimation, and that will be one of our first examples for a parameter estimation, we try to find the values of the parameters that fully determine the density of a certain random variable. If you don't know that value p, then the random variable is useless. You know it in general, but what's the use of it? The percentage that the candidate will take in the elections can be anything between 0 and 100. So what? We know that. That's a fact. The question is that person electable or not? Is that person going to be elected or not? Is the P going to be greater than 0.5 or less than 0.5? Those are the questions they dwell in. Essentially, those are questions that statistics provide as tools to answer. All right? So that's exactly that is a prelude for the upcoming statistics part. So now, do we understand here? I don't really have too many things to do because the random variable is very trivial. It takes only 2 values. And it's quite nice, actually. This is the Bernoulli random variable, and its associated binomial distribution offer a very nice model for modeling, actually, a lot of activities. One is the stock market. I will show you a very simple example of the stock market modeling. Very simple. We're not going to do serious things. I do more with the 30-38 course when we come at that particular chapter. What is the expected value of x? Well, let's calculate that. What is the mean value of x? X takes only 2 values. But what is the mean value? What is the average value of x? Well, by definition, this is x times the density. So here, that's value of the random variable. And that runs throughout all values, the sum. So what does this sum boils down to? Here, our random variable has only 2 values, 0 and 1. So I will have 0 times f sub x of 0 plus 1 times f sub x of 1. 0 times the value of the density at 0, which is one of the 2 values, plus 1, that's the other value, times the value of the density at 1. Well, the first term will obviously give you 0. The second term will give you 1 times p. So the value is equal to p. So the average value of the Bernoulli random variable is equal to p, the rate of success. Okay? So here you have one first and very simple example of this calculation, of the mean value calculation. Let's calculate something else. Let's calculate since we have a very simple example, let's find the standard deviation of x. So I'm summarizing my result with rate of success or with probability of success equal to p. Okay, let's find now the standard deviation of the Bernoulli random variable. First, we have to find the variance. What is the variance of x? Well, the variance of x is the expectation of x squared minus the square of the mean. Well, let's find the expectation of x squared. I haven't taught you how to do this, but this is exactly by definition. That's the definition of the second. This is called, by the way, the second moment of x. And that's the definition of the second moment. X runs, as always, throughout all the possible values of the random variable. Now, we multiply the value squared times the value of the density that corresponds to the specific value of the random variable. No, we'll see what it is. Well, let's do it. We have only two values. So we have 0 squared times f sub x of 0 plus 1 squared times f sub x of 1. And what is this going to give us? P again, correct? So what is the standard deviation? What is actually the standard deviation of, what is the variance of x? Well, we take p minus p squared, correct? Which is p times 1 minus p. What is the standard deviation of x? Well, it's the square root of the variance, and that is equal to the square root of p times 1 minus p. And as we said, the variance gives you how much variability you have. It expresses the variability. How much, in average, the values will differ from the central value. Okay? So that's a very simple example. Well, let's do another example. This is the discrete uniform distribution. What I will do. Okay, now from now on you will hear me using the terminology discrete, uniform, or whatever, blah blah, binomial, and I will be using the term distribution. So that means not a distribution function, but it means specific probability model. And the model is being specified by the modifier, discrete uniform here. So what is this here? X, that's how things will start. X, a random variable, which takes values, let's give it values 1, 2, up to n, has the discrete uniform distribution. If the classical probability model prevails, if, how many values does it have? It has n values. If f sub x of I is equal to I over n, where I is 1, 2, or n. So I assign exactly the same value, the same probability to each value of the density of the random variable. That's what we say the uniform distribution. Essentially, it tells us that we don't really know anything about this random variable. We have no information. All the values can be equally likely. Everything can happen. All outcomes are completely open. The fact that you assign the uniform distribution, it's expressing your utmost uncertainty about the outcome of X. You really have no real insight in the random variable. Okay? So suppose that X takes the values from 0 to 255. For obvious reasons. What would be the model that would give you the discrete distribution? Up to 255. So it would be this. This is grayscale model for 1 pixel. For whom you don't really know anything.
Wait, wouldn't that probability not add up?
What?
Since x equals 0.
Oh, no. One, sorry, it's not I, it's 1 over, correct. You're right. That's 1 over. Yeah, because then all values are possible. Okay, let's see, what is the probability that x will take values now between 12 and 40? What shall I do? Well, see the formula we used before. Look here. I have to sum the values of the density function that correspond to the input x, the value of the random variable being between 12 and 40, according to this formula. So that will become the sum to 40 of f sub x of x. Now, all those values are equal to 1 over 56. How many values do I have? So that will be 40 minus 12 plus 1 times 56, divided by 56. So that will be 40 minus 29 over 256. So that is this probability. If, on the contrary, I ask you this, what should be the range of this sum? The upper limit should be 39 because I'm not including 40 in the range of the values. And the random variable is discrete, takes the value 0, 1 up to 255. So that forces to stop at 39. And this again would be 39 minus 12 plus 1 divided by 246. So that would be 28 minus 2 divided by 256. What? The additional one? Okay, how many terms do I have if x goes from 12 to 40? It's like, no, 28 plus 1. It's like the following. If you have the straight line, you have 1, 2, 3, 4. What is the difference between 4 and 1? Well, the difference between 4 and 1 is 3. Everybody knows that, okay? And that's the length. But how many numbers do you have if you start counting from 1 all the way to 4 inclusive? 1 and 4 inclusive 4. That's exactly what forces me to add 1. Huh? Yeah, I have to count also the initial number. Or initialize. I initialize at 12. So I have to count 12 as well. If you don't want to count 12, it's just a difference. So, for example, if you had p between 12 less than or equal to 40, then you can count just like that, because you start at 13. Then will be 39 minus 12. And 12 is what? 13 minus 1. Yeah, or 40 minus, yes, that would be 40 minus 12. I copied from the 40, yes. Is it clear? Yeah, I had in that last one, I had strictly less than 40.
Oh.
So 40 was not included. Okay, be careful to properly interpreted notation. Now, with this example, I want you to find the distribution function, what we call the cumulative distribution function, CDF. Or simply distribution function, hence the term distribution I used before. Of X. So what is this function? Again, we use the uppercase F and the subscript X to indicate the random variable. That's a function that is defined for every real number, and it represents the probability that X will take values less than or equal than A. Let's say, what is the value of the distribution function for 128? That would be the probability that takes values X less than or equal than 128. So which is the sum now I have to do? Which is the range for the sum? I start at 0. I have to exhaust to take all values that are of the random variable that are less than or equal than 128, up to 128. How many values do I have? 129 divided by 256. All right? So what is the distribution function, the value of the distribution function on 127.3? What is the range? 0 to 127, okay? 127.3 is not a legitimate value of the random variable. The next value is 128. So you stop summing at 127. And that will give you one less.
So cases like this is truncation, no rounding.
Of course, no. I mean, of course you will truncate. And essentially the graph will be like this. We've shown this before. Here you have 0. That's the vertical line. You will only go to 1. You will have 1, 2, 3, 4, 5. Okay. And at the beginning it will be, I will use the red. It will be 0 here. Here you first jump to 1 over 56. You always have these open circles at the end. And so forth and so on. Okay? And this is 1 over 256. This is 2 over 256. And these jumps here are equal to 1 over 256. That's how it works. Okay? Mm-hmm. Yeah, now if we don't have a discrete, whenever we have a discrete random variable, always the distribution function will have this stairwell, will look like a staircase. And it cannot exceed 1. When you will hit 255, then you hit 1 and it stays equal to 1 from that point on, okay? Flat equal to 1. Now, associated to the distribution function, there are a few other things that we need to mention. The median and the quartiles. Later on, when we'll do continuous random variables, we will introduce more the quantiles as well. So the median of a random variable, discrete or continuous, the definition is the same, is, we call it Q50 because it's the 50th quantile. The median is defined by the following equation. It's the point where the distribution function takes the value 0.5. So that's the median. And the first quartile so that's the first quartile. And the third quartile is Q75. So what should be the median for that uniform distribution that I had before, for this X? Okay, so we try to find what is the number Q50 that will satisfy this. So what that is, well, this is the integer value of Q50 plus 1 divided by 56. So this number is the smallest integer, what I put in the brackets. No, sorry, the greatest integer less than or equal than Q50. Okay, you can start, we can start, investigating. Let's see if Q50 is equal to 128. Would that work?
Not quite.
Not quite, because it's 128 plus 1 divided by 256. You're slightly over than 0.5. So that's not a good choice. What's another choice? 127. Okay, so does 127 work? That's the middle value, okay? So 127 does work because you have 127 plus 1 divided by 256 is equal to 0.5. So it does satisfy this equation. Now, how many numbers are on the left? Let's see what is 255 is here, and 0 and here is the 127. How many values of X are less than 127? You go from 0 to 126, so how many are they? 127. How many values are on the right of 127? You see, you leave half of them on the left, half of them are less, and half of them are greater. And that's exactly the median. That's how you find the median exploratory analysis. Yes? That is the middle one. Yes, that's the middle, that's the median. So the median is supposed to be in the middle of the range. Now, for the uniform distribution, now let's compare the median with the mean value of the discrete uniform distribution. What is the mean value of the discrete uniform distribution? Which should be the range of the values that I have to sum? What have we said when we calculate the mean or any moment, the second moment, the third moment, and so forth? What do we do when we have this E here, expectation? We sum over all possible values of the random variable. So what is the range of the summation? X will go from 0 to 255. Okay? So we have so what is this thing here? It's 1 over 256 times the sum. Do you know how this is calculated? What is this actually? How do we call it? This is a partial sum, okay? This is a summation. But what can we say about the terms of the summation? How do we call the terms of the summation that we sum? In calculus, you didn't like that calculus. You got some problem with it. Sort of a traumatic experience. You want to erase it from the hard drive. How do we call it? Each term differs from the previous term by what? By 1. How do we call the terms of this sequence? No. The series go all the way to infinity. You have an infinite number to sum. No. You have an arithmetic progression here. Each term is equal to the previous plus a fixed increment. And the fixed increment is 1. So this thing here is equal. You have the first term is 0. The last term is 255. Okay, so you have the sum from first term. I'm not summing from 0 because 0 plus whatever doesn't change. I start from 1. First term is 1. Last term is 255. No, I'm not taking the average. I'm trying to calculate this. This is equal to 255 times 255 plus 1. Okay, we can't squeeze it, obviously. So what is this equal to? 127.5. Slightly different than the median, but very close. Okay? Is that clear? How we find this? And I'll let you work the standard deviation. The variance of x first, and then the standard deviation of x. Those are good examples for practice. Okay, now I will ask first of all if there are any questions so far. Do you have any questions? Do you understand everything? Yes.
So what was that sum called? You're asking what the sum was called?
Oh, the sum, if you sum, the sum that I used, you sum all integer numbers from 1 to m is equal to m times m plus 1 divided by 2. So that's what I used. 255 times 255 plus 1 divided by 2. What? Oh, you did that in calculus, arithmetic progressions. You did them in calculus. Those are special types of sequences, where the next term of the sequence is the previous plus an increment, a fixed increment. Those are arithmetic progressions, and you have arithmetic, geometric, and harmonic progressions. I don't think you did the, no, it's not the same. But I don't think you did those harmonic progressions. I don't think we do them. I haven't taught calculus 2 for a while. For a long time. That was, I think, the last time I did it only once. And it was horrible. It was a horrible experience. I don't envy anybody who has to teach calculus 2. Because it's a killer course, especially in this university. Primarily because the students don't have good algebra skills. At least the time when I taught it. And yeah. So now we go to the binomial distribution. I needed this intermezzo. Do you know what an intermezzo is? No music majors here? An intermezzo. Well, in the opera, you need sometimes to change the stage set between the two acts if you don't have an intermission. So in this case, you have the medical, you have the intermezzo so people can get out of the stage and other people can come in, or you can have a minor modification. And what happens is that the orchestra plays and there's no singing. So that's the intermezzo. So after this intermezzo, we start the binomial distribution. And what is a binomial distribution? So yes.
What's the secret for summing up numbers like these basic for when they are linear, but what about when they're square?
That's different. I don't want to touch it now. Don't worry about that. That's a complicated formula. There's no point
So
right now.
solve this?
You can. It's in your calculus text. It's in your calculus text, and it has a little bit of difficulty to calculate it. It's not a point. It's not what I want to do in this course. Okay, and it doesn't worth it. Just take the damn formula and find it. And don't ask me right now because I don't remember it on the top of my head. I don't really recall this formula. But there is a sum where instead of x, I have x squared, and there is another sum where instead of x, you have x cubed. And those are the only formulas that I know of this kind. I haven't seen others. Okay, let's go to binomial distributions. We say that x, a discrete random variable, has the binomial distribution with parameters n and p. Now, n is a positive integer. P is probability of success. That's what it will turn out to be. And the value of the p will be between 0 and 1 as before. If its density function is the following: n choose x p to the x power 1 minus p to the n minus x, where x takes the values 0, 1, 2, all the way up to n. So implicitly what I'm telling you here, I'm telling you the following things. 0, 1, 2, and n are the values of the random variable, and the density function is given by this formula. Okay, now I understand that this sounds way too abstract, so we have to make it more understandable. Let's see what are cases where we have the binomial distribution. Cases where we have the binomial distribution, or when do we have the binomial distribution? Let's see.
Tossing a coin enough times. Tossing a coin enough times.
Tossing a coin or executing an experiment. So we have x is the number, so that's when we have the binomial distribution, when x is the number of successful, whatever you want to call success, trials in a series of n independent Bernoulli trials. Okay, let me give you some examples to make that easier. In Bernoulli trials, I forgot something, all with the same probability of success. Because if the probability of success changes, we don't have the binomial distribution. Now, look here. Do you see n? My first of the two variables, of the two parameters that determine the model, and this other one, p. P is the rate of success, the fixed rate of success per trial, and n is the total number of trials we perform. And all of those trials must be independent. So the outcome of one trial does not influence the outcome of any other trial. And when do we have that? Typical example, coin tossing. We toss a coin 200 times. That's my n, 200. Each time you toss the coin, the result does not depend on the outcomes of the previous ones. Therefore, the trials are all independent. And when you toss the coin, the probability of success, say tails is success, you don't change the success per experiment. What you call success should be the same throughout all of those trials, is the same, equal to 0.5. So that's a typical example of a Bernoulli trial. Another example, families try to get boys, like Henry VIII was trying to get boys, and he was believing that by changing wives, finally had to change the Church of England to accommodate that need, would give him a boy. Well, he didn't know that no fathers truly determine the gender. Mothers contribute both genes, but fathers are the ones who have the homozygote. Okay? Therefore, that's, again, you can consider that it is a series of independent Bernoulli trials, and for simplicity, we assume that the gender, let's say success is a boy, well, women would probably disagree, is the same 50% in all of those trials. So that's another example. A more important example, probably for those who want to look at the stock market. X is the number of up movements of a stock in the stock market in a period of n trades, independent trades. Okay, that's a very interesting model because it allows us to model what will be the value, what will be the expected gain or loss in a stock. And therefore, if that stock is a bond, then we use this simple model to calculate what should be the anticipated credit default swap, the cost for the credit default swap. Do you know what is a credit default swap? No? The CDS, credit default swap. It's pretty much like the PMI you pay in the mortgage. No, why the mortgage? Why did people get into trouble at the first place? In this market, because they gave them those adjustable mortgages, okay, and then the mortgage had high rates. Why does a mortgage has a high rate? Yeah, if you are credit worthy, everybody wants to give you money. Because it's the easiest form of investment. You don't have any, you have just a stupid computer like this one, and you give the money and you make money. You don't have to build a company, to hire employees, have human resources, pay the social security, pay accountants, nothing. With a simple computer and internet connection, you can make money. That's why banking and investment became such a big thing in the time of computers. So if you have a lot of money and you need a little bit, everybody wants to give you money because you are credit worthy. They expect they will get their money back. Well, the same with countries. So bonds, sovereign bonds, as we say, sovereign debt issued by sovereign countries, it's considered to be highly liquidable because you can always exchange it for money. It has such high credit worthiness that it's always exchangeable, even in the easy day. Suppose that you want to pay your employee, you want to pay Social Security. Suppose that the Social Security doesn't have enough liquidity one day. Do you know what they will do? They will put their bonds as, they will actually pawn their bonds. That's what they do, and that's called repos. And they take a short-term loan with guarantee the bonds. And when they will repay the money, as people will go back to the pawn shop and take their watch back, when they give back the money, they will take back the bonds. So bonds are very nice and they're highly liquidable. Well, until we had the European crisis and especially Greek crisis, we believe that bonds are highly secure. That's why at the end of your retirement, you keep bonds. You don't keep stock in your portfolio. Because bonds give you those so-called coupon. And with a coupon, you make money every year. And at the end of the term, you get your money back. If you calculate the accrued interest you paid each year with the so-called coupon, the 5%, the 2%, right now the government, the United States government, for some short term, has even negative interest rate. They park money. They pay the federal government to park money in the short term. Those who have a lot of cash, and there is people with a lot of cash to park. So the coupon represents a return of investment which is guaranteed every year. And at the end, if you add all those coupons that you have collected, all the interest, plus the amount that you pay at the liquidation, at the maturity day of the bond, you get your money plus something else, a profit, and that's the so-called yield. That determines the yield of the investment, of the bond. So when we feel that this is not very good, or when you want to hedge against a possible default, somebody doesn't pay the mortgage, you buy the so-called credit default swaps. So what you do is that you enter a contract with someone, and you say, okay, if I pay you this amount of money, and that's all basically the expected value of the binomial distribution in the simplest form. I pay you this amount of money in form of a guarantee. If I lose my money, my investment, my initial investment, let's say the bonds of Greece, if Greece won't pay me back, you pay me back the value of the bonds, the nominal value of the bonds, the value that the bond has been issued at. So this is a credit default swap. So what's your cost if you buy the credit default swap? It's like an insurance. You buy some insurance for your investment as you buy insurance for your car. If you lose, you just lose the interest or part of the interest. You don't lose your initial capital. So that guy who sold you the credit default swap will have to pay you. Well, they make their calculations. Now, what these guys do as well, they do the same thing as you did. And now it goes to somebody else, repackaged. And then it goes to someone else, repackaged. And then it goes to someone else, repackaged. And everybody sells. Well, there was one stupid who was insuring as the last one. Who is going to be, in the case of the default, the one who will be truly suffer the F word? The one who is the last. And how can we find the last? Well, if the initial one who has to pay defaults, then everybody exercises the so-called option of the contract. And everybody calls them and say, okay, you owe me, you call your next guy who insured you, and everybody calls everybody, and everybody gets paid, some lose some money, but somebody loses a lot. Well, AIG had actually insured many of them. And who did back up AIG? Well, in full capitalism, unfortunately, the federal government, who doesn't, of course, for many years, for several years, didn't help people to get out of foreclosure. AIG should have been foreclosed probably 1,000 or 2,000 times. For all this money, all those contracts that basically were insured by AIG, credit default swaps that were insured, and they were the last ones. So this is the main idea. And how do we calculate this? It's the expected value of the binomial distribution. What is the critical thing for this expected value? I'm not going to make the calculation. The expected value of the binomial distribution is n times p, where p is the probability of success. So if I know that my bond goes up or my stock goes up, what is the expected rate of return at the end? It will be n, how many times I trade it, times the probability that it goes up per trade. That's the stable model. The market doesn't work like this, because the stable model has one assumption. That is a very simple, the simplest, the stupidest, naive model. The more complicated model is the so-called Black-Scholes formula that assumes one thing, that always the market will operate under full liquidity and where the speculators work independently of one another. So essentially all stocks move independently of one another because the speculators. The speculators are those who do the trading. But if, as we see, when the rats go all to the door, they go all and they run very fast. They all sell or they all buy. For unknown reasons. Nothing was happening to Greece. Greece was credit unworthy and they were selling like crazy. The next day or 2 days later, Greece was again unworthy, credit unworthy, and again they were buying like crazy. I said, what has changed? Nothing had changed. So this is exactly how the credit default swaps work, and this is one of the very, very important uses of the binomial distribution model. It models in a very simple way the move of bonds and stocks and the gains. So what would be overall your gain if you had 200 trades and your stock would go with up or down, 50% up or 50% down? Not value, can go up by 50%, 50% will be increased, 50% will be decreased. Now, whenever we have this, per trade, you say it goes up by, let's say, 0.01%, 1%, or it goes down by 0.02 or 0.03. You can say this with probability 50% and this with probability 50%. So I know pretty much what the movement is. I don't know how likely it is to go up or down. So I assign equal probabilities here. In how many, if I do 200 trades, what is the expected number of going up? 200 trades with probability of going up 50% per trade will be 100 trades. At 100 trades, I will go up, and what is the gain each time? 0.01. So roughly, I go up 1 by 1, by a factor of 1. So this is a little bit more complicated. You go up by 1% per time. So what do I speak about right now? Amortization or compounding. So you need a compounding formula. So that's more complicated. But I'm telling you that this is a very useful model for financial mathematics, simple financial mathematics. And remarkably, it's being used for stock modeling. Okay? Well, I don't know what time it is right now. Oh, we need to get out of here. Okay, and that's all for, marketplace tutorial today.